Let's now talk about the use of electrolysis and electrolytic cells. Electrolytic cells are ones which use an external voltage and a current to force a non-spontaneous reaction to occur, right? So this is distinct from a galvanic cell, which contains a spontaneous reaction. In an electrolytic cell, you have a non-spontaneous reaction occurring, and you need to therefore provide an external influence in the form of voltage and current to force the reaction to occur. This has a lot of important applications to us. So one might be electroplating metals like gold. You could do this if you wanted to make relatively inexpensive jewelry, right? For instance, a solid gold piece of jewelry would be very expensive. But if you were to take a piece of jewelry that was made out of like stainless steel or aluminum, that would be much cheaper. And then you can plate a thin layer of gold on the outside so that it looks really fancy and it looks really expensive, but it's at the fraction of a cost because it just has a very thin film of gold on the outside. You would use electrolysis to put that thin film of gold on the outside. Another application might be separating water into its elements, H2 and O2 gas. And the advantage of doing that is H2 gas is being considered as an alternative fuel source for cars. Like right now, most cars use gasoline as a fuel source, but eventually we're going to run out of gasoline. And when you combust gasoline, that produces greenhouse gases and a bunch of things that aren't good for the environment. Now, water is pretty readily abundant, and so you could take the water and you can electrolyze it and separate it into its elements. You can then isolate the H2 gas, and you can use that as the fuel for your car. It then gets combusted inside of a hydrogen fuel cell in the car, and that provides the energy that's required to power the car. And when you combust the hydrogen gas in the car, your product would be water, which is much more friendly to the environment than when you're burning fossil fuels and producing a bunch of greenhouse gases and things that are really kind of not so good for us. And the last application of electrolytic cells or electrolysis would be in the recharging batteries, as I described in the previous video. So when you discharge the battery, right, you're operating the battery in a galvanic cell mode as you're doing the spontaneous reaction that occurs. But then when you want to recharge the battery, you have to force the reaction to go in reverse, right? That would not normally be spontaneous. And so you need to provide this external current and voltage by plugging it into the wall to get the batteries to be recharged so that you can use them again and again. Let's talk a little bit about units when we're dealing with electrolysis problems and electrolysis calculations. Since we need to use an external electrical current, it's helpful to talk about how one could calculate current. And we have this equation here that says that current, that's what I means, is equal to the number of moles of electrons that are transferred times Faraday's constant divided by time. Now, current is defined as being the amount of charge that's being put through the cell per unit time. And for current, which again is represented by I here, the currents will be amps. It's capital A. Now let's talk a little bit more about what amps represents. So in this equation, in the numerator, you have N times F. So let's think about the units that we have on that. N is the number of moles of electrons, and F is coulombs per mole of electrons, right? So the moles of electrons cancel out, and so the numerator has units of just coulombs. And on the bottom, we have time, and for time, we're going to use units of seconds. And so what that tells us is that an amp would be the same thing as 1 coulomb of charge being passed per second of time. And that introduces what the units are here, and that also gives us an equation that we can use for doing problems that involve current flow. Let's take a look at an example here. We're asked to determine how long it will take to plate out 10 grams of solid nickel from a solution of Ni2+ using a current of 100 amps. Let's start by recognizing that a chemical reaction is occurring. We're taking Ni2+ and turning it into solid nickel. So let's write the reaction. Anytime a reaction occurs, write it out. The reaction is going to be Ni2+ is what we start with, and we're going towards producing Ni solid. This equation has to be balanced for charge, and so we have to add 2 electrons to the left-hand side of the equation. Now, for doing electrolysis, to relate the current and the time and the amount of nickel that you're trying to produce, we can use our electrolysis equation, I is equal to NF over T. And the problem is asking us to solve for time, so we can cross-multiply through this equation to solve for time, and get the time is equal to NF over I. Now we need to think about the numbers in this problem, what we're going to plug into this equation so that we can get our answer. We know what Faraday's constant is, right? That's 96,485. We know that value. And we know what the current is, 100 amps. But what does N represent, right? This represents the number of moles of electrons that get transferred. Now, when I look at the reaction, if I use the coefficient of 2 for 2 moles of electrons, will that be answering what this problem is? If I use 2 as the number of moles of electrons, am I going to answer the problem and produce 100 grams of nickel? The answer to that is no, because this balanced equation that we have here tells you that for every 2 moles of electrons that you use, you're going to make 1 mole of solid nickel. That's not 10 grams. And so what we need to do now is perform some stoichiometry to convert the 10 grams of nickel into a number of moles of electrons that we can use in I equals NF over T. So that's our third step, is to do stoichiometry to find the number of moles of electrons that are needed. Because this problem is specifying that you need 10 grams of nickel. So 10 grams of nickel can be converted into moles of a nickel by using the molar mass. 1 mole of nickel is 58.7 grams. All right, and now you can convert the moles of nickel into moles of electrons using the balanced reaction that we've written here. 2 moles of electrons are needed for every 1 mole of nickel. And now, having done the stoichiometry, we can convert everything and get what the value of N should be. This comes out to 0.34 moles of electrons. That is the value of N that we should use in this problem. And that, again, is because we're not trying to produce 1 mole of nickel, we're trying to produce 10 grams of nickel. So you had to do the stoichiometry in order to convert that into moles of electrons. All right, last thing for us to do is to solve for T. All right, so we said that T is equal to the number of moles of electrons, which we now from stoichiometry determined was 0.34, times Faraday's constant, 96,485 coulombs of charge per mole of electrons, over the current of 100 amps. And it'll be hard to see how the units cancel out unless you remember here that 1 amp is the same thing as 1 coulomb per second. So instead of saying 100 amps, I'm going to write it as 100 coulombs per second, and that will help me to see how the units cancel properly. The moles of electrons cancel, and then the coulombs cancel from the coulombs in the amps, and I'm left with just units of seconds. And the amount of time in seconds comes out to 328 seconds. That's how long it would take to plate out 10 grams of nickel from this solution using a current of 100 amps. All right, next up we'll talk about how you can predict whether or not a reaction is spontaneous.